Hello, everyone. Welcome to the algebraic graph theory seminar. Today, Theo McKenzie from Stanford University will tell us about precise eigenvalue location for random regular graphs. Theo, please.
Sure. Yeah. No, thanks so much for the invitation. It's really nice to be able to talk to all of you today. Today I'll tell you about some recent work about spectral graph theory, where we use a series of matrix inverses to get very precise locations of eigenvalues. Uh, Let me just say it's my goal in this talk to give a very general overview because I know that people are coming from diverse backgrounds. So definitely, if anything is unclear during the talk, please ask a question, and I'm happy to go into as much detail as is necessary. So this is joint work that I did with Jiayang Huang, who's a professor at the University of Pennsylvania, and Hongsir Yao, who's a professor at Harvard. All right, so just general outline, we'll just talk about some motivation for the problem. Then we'll go through some of the methods just to give you an idea of how to solve something like this. And then I'll also want to touch on some future directions as well. Okay, so starting with motivation. So this is going to be a talk about spectral graph theory. Okay, so the general object that we're working with is the adjacency matrix. So every graph has an adjacency matrix. I have rows and columns that correspond to vertices. I put a 1 in an entry if there's an edge between the two vertices. I put a 0 if there's no edge between the two vertices. And historically speaking, there's been a very nice interplay between these two interpretations. First of all, if I look at the eigenvalues of the adjacency matrix, this gives me a lot of information about the geometry associated with the graph. And conversely, oftentimes when I have some kind of matrix problem, some problem in linear algebra, it can be convenient to think about it as a graph problem and think about the geometry of this matrix and namely change it into some kind of spectral geometry question. So this is the type of interplay that we'll be talking about today. So the model specifically that we're working with is going to be the random regular graph. So this is often used when we want to create some type of network which is very, very sparse. So the degree of vertices is low, but still it maintains strong connectivity properties. And this is a ubiquitous model that's used in a lot of different areas. And there are many ways to think about the random regular graph, but one way that we can generate it is I fix the number of vertices, so I'll just call that n, and then I'll fix the degree of every vertex, I'll call that d. So there are going to be a finite number of graphs that are on n vertices and have degree d, and so I can just think about sampling one uniformly at random. So it's like I take all of these graphs, I put them in a giant bucket, and then I pick one out uniformly at random. So I've written here a random 20 vertex 3 regular graph. So you can see there are 20 vertices. Every vertex neighbors exactly 3 other vertices. And something that we'll do in this talk is that we'll actually, instead of the adjacency matrix, we'll think about the normalized adjacency matrix, which will just be convenient to compare this matrix for different values of d. So I'll denote that by h, and this will just be a over the square root of d minus 1. Okay, so if I consider this operator h, then I have a real symmetric matrix. So all of its eigenvalues are real. And moreover, it's not so hard to check that the largest eigenvalue will always be d over square root d minus 1. So this corresponds to the all ones vector. So this is just the normalized version of the all ones vector here. And the idea is that if I look at any vertex, I receive exactly d copies of itself from other vertices, and then I've done this normalization by square root d minus 1. So the top eigenvalue is always this, and you can also show that this is the largest eigenvalue by the parent-Frobenius theorem. So In terms of spectral statistics that we're interested in, one that people often care about is the spectral gap. So we can think about this as the maximum between lambda 2, so the second largest eigenvalue, and minus lambda n, which is the most negative eigenvalue. And the point is that this second largest eigenvalue gives the mixing time of the random walk. And often people are interested in this as this encodes some kind of combinatorial expansion. And so our goal for this talk is going to be to give a very precise description of the spectrum associated with this random regular graph. Okay, so first we can think about what's called weak convergence of the eigenvalues. So the idea is that if I take larger and larger random regular graphs with fixed sparsity, then locally, for many vertices, the neighborhood is going to start looking like a tree, like the right-hand side here. And what that means is that if I look at the moments of the random regular graph, those will converge to the moments of this operator, this infinite regular tree. And what that means is that if I look at the distribution of eigenvalues, then that will converge to the eigenvalues associated with this regular tree, which is something explicit that has been studied for a while. And specifically, that's called the Keston-McKay measure. So Harry Keston calculated the spectrum for the deregular tree, and then Brendan McKay proved convergence of high girth regular graphs to this spectral distribution as well. And specifically, the spectrum is given by this formula that I've written on the right-hand side here. So in the middle of this slide, I have a plot, which is actually two plots superimposed on each other. So the blue line corresponds to what's given by the Keston-McKay law. So theoretically, what's predicted in this model. And then the red histogram gives the eigenvalue distribution for a very large random regular graph. And what you can see is that these two objects are very, very close to each other, even for this finite d, for this finite n. However, there are a couple of things that I want to note about this. The first thing is that when I look at this spectral measure here, it will never witness the top eigenvalue. So what we said on the previous slide is that the top eigenvalue is always equal to d over square root d minus 1, whereas this measure is only supported from -2 to 2. So that doesn't matter though, because what we're interested in here is just weak convergence. So we can ignore an individual eigenvalue. So for example, in this plot, you can see on the right-hand side, I have just one eigenvalue, which is outside of the spectrum, and this corresponds to this lambda 1. The other thing that I want to note is that as d goes to infinity, this spectral distribution converges to that of the semicircular law, which is to say that if you look at this formula at the top, then the dependence on d is contained in this term in the middle. And as d goes to infinity, this will converge uniformly to 1. And what I'm left with is something that looks like a semicircle. And the semicircular law is something that shows up a lot in random matrix theory. And actually, the relationship between the Keston-McKay law and the semicircular law is going to be very important when we try to figure out the spectral distribution associated with these graphs. Okay. So let's focus on the largest eigenvalues. So what we're going to show specifically is that along with weak convergence, actually the Keston-McKay law is going to determine every single eigenvalue in the spectrum in some very strong way. So thinking specifically about these edge eigenvalues, so lambda 2 and minus lambda n, the Allen-Vopana bound gives that these eigenvalues are always at least 2 minus some function that goes to 0 as n goes to infinity. So what this means is that these eigenvalues always cannot be too much smaller than 2. And if you look back at the previous slide, this is in line with this Keston-McKay law, because what it's saying is that these edge eigenvalues can't be too far inside of the spectrum here, where the limits here are 2 and -2. Okay, so if we want a very good spectral expander, we want these numbers to be as small as possible. So Lubotsky, Phillips, and Sarnak called a graph Ramanujan if it was an optimally good spectral expander, which is to say that for any eigenvalue that's smaller than d over square root d minus 1, it's actually smaller than 2. So I have this very large interval in which I see no eigenvalues. And the point is that by this Allen-Lopana bound, this is really the best possible spectral expansion. Now, Ramanujan graphs really come in two types. I can think about a non-bipartite Ramanujan graph, in which case I have one eigenvalue of magnitude d over square root d minus 1, and all the other ones are contained in this interval -2 to 2. So that's like the left-hand side here. The other option is that I have a bipartite Ramanujan graph. In this case, I have two eigenvalues of magnitude d over square root d minus 1, and then all other eigenvalues are contained in this interval. So these are the two general types of Ramanujan graphs. So in this original work of Lubotsky, Phillips, and Sarnak, they generate examples of both of these graphs, of both non-bipartite and bipartite versions, using number theoretic techniques. Specifically, they find specific Cayley graphs that have these properties. So Margulis independently, the same year, published a paper also coming up with examples of these types of graphs. And specifically, these are Cayley graphs. There are specific examples for when d is equal to p plus 1, where p is some prime, and then generating graphs with that d. So Morgenstern generalized this Lubotsky-Phillips-Sarnak construction to work for when d is equal to p to the k plus 1, where k is some integer. And then Marcus Spielman and Srivastava in this series of works used non-number theoretic techniques to find examples in the bipartite version for any d and any n. So I'll note too that, okay, even for these number theoretic constructions, I have constraints both on the degree and then for fixed degree. There are basically infinitely many n for which I can create a Ramanujan graph. But if I just choose a number at random, there probably won't be a construction. Whereas for this last one, this really works for any degree and for any n. So this completely solves the existence problem in the bipartite case. However, the non-bipartite Ramanujan graph question, so something that looks like the left-hand side, has remained open. And I just want to note that any example of non-bipartite Ramanujan graphs would actually also give us further example of bipartite ones by taking what's known as the bipartite 2 cover. Okay, so this is basically the state of field in construction of Ramanujan graphs. And what about a random graph? So let's go back to that example. Are these Ramanujan? Well, Noga alone conjectured that with high probability, a random regular graph is going to be what's called almost Ramanujan, in the sense that if I look at these eigenvalues, lambda 2 and minus lambda n, they're going to almost satisfy this Ramanujan bound, where it's 2 plus, once again, some function that goes to 0 as n goes to infinity. So this was a famous conjecture in combinatorics for many years, and it was proven by Joel Friedman using a very precise version of trace arguments, basically estimating the trace of very high powers of these random regular graph adjacency matrices. And specifically, if you follow the proof, what he shows is that the second largest eigenvalue is always at, or with high probability, is at most 2 plus O of something like 1 over polylog n. And this is given an alternative proof by Charles Bourdanov, also using different types of trace arguments. So later on, my collaborators, Jiaoyang Huang and Horngser Yao, improved this to show that, in fact, the second largest eigenvalue is always 2 plus 1 over polynomial. And actually, they showed something stronger, which is that with high probability, every eigenvalue, lambda 2 through lambda n, note that we're throwing away lambda 1 because we always know where it is. But every other eigenvalue, lambda 2 through lambda n, is very close to where we would expect it to be. Now, where would we expect lambda k to be for some index k? Well, the idea is that at lambda k, 1 minus k over n of my spectrum is to my left. K over n of my spectrum is to my right. Right? That's another way of saying what the kth eigenvalue is. And so we have a prediction on that based on this Keston-McKay law. Specifically, I have this number gamma k such that if I look at the amount of spectrum from minus infinity to gamma k, that should equal 1 minus k over n. And what Zhao Yang and Horxer show is that every eigenvalue is very close to this prediction based on the Keston-McKay law. Okay, so here we have these improving bounds, but what do we actually expect to be the right answer, right? Like what's the actual rate of fluctuation of the second largest eigenvalue? And Miller, Novikov, and Sabelli ran this large number of computer tests to try to figure out what the distribution of the second largest eigenvalue was in this random regular graph model. And what they found, and this figure comes from their original paper, is that up to some renormalization, the distribution of lambda 2, for example, approximates the distribution of the largest eigenvalue for a Gaussian matrix. So this is just some n by n matrix where all the entries are Gaussian. And this has the distribution of the largest eigenvalue has a specific name, namely it's called the Tracy-Whittem distribution. And specifically, these computer tests led them to conjecture that for every d, there are some constants C1 and C2, such that if I renormalize my distribution, so I take lambda 2, normalize it at 2, multiply by n to the 2/3, and then C1, and then subtract away C2, that this will converge to the Tracy-Whittem distribution. Okay, let me just note that this conjecture has already been known for if I allow d to increase as some polynomial function of the number of vertices due to these various works. However, I suppose what we're interested in terms of this talk is for when d is fixed, so when d is some constant. Okay, so let's highlight a couple of things about this conjecture. So first of all, if this conjecture were true, and if C2 were equal to 0, then this would mean approximately 69% of all graphs were Ramanujan. And the point of this is that if I look at the probability that Tracy-Whittem is less than or equal to 0, then this is like 83%. So if I square that, it's 69%. So that would mean if this conjecture were true and C2 were equal to 0, that I would just need lambda 2 to be less than 0 in this normalized version and lambda minus lambda n. And so the probability of that is 69%. So in fact, this thing that's been a bit tricky to find, which is this Ramanujan graph, is somewhat common in the sense that a majority, in some sense, a majority of graphs have this Ramanujan property. The second thing that I want to note is that according to this conjecture, the correct rate of fluctuation of lambda 2 should be something like n to the minus 2/3. Right, so this originally Friedman proved 1 over polylog and then 1 over polynomial. The correct rate of convergence should be something like n to the minus 2/3 plus little of 1. Okay. So I just wanted to give a big picture perspective on why is this problem hard? Like, why is it hard to construct these Ramanujan graphs? And this is just this is mainly just my opinion, right? But I think the point is that we only have some small number of tools to actually think about the spectrum in proper levels of specificity for arbitrarily large sparse graph. And really, these types of tools really don't generalize well to thinking about this problem, even though it's conjectured that a majority of graphs have this property. So some things that I might try to do, right? Like think about embedding my graph in Euclidean space. Well, that's always going to be about expander. If I want to use number theory, then as we saw, then I really need strict requirements in terms of my degree and also in terms of my number of vertices. So that doesn't generalize that well. Marcus Biilmann-Srivastava, this is a very novel, innovative method, but we can only really use it to bound one eigenvalue at a time. And the Ramanujan graph question, at least the non-bipartite version, we want to bound both lambda 2 and minus lambda n at the same time. So it doesn't seem amenable to that. And if we want to reason about a random graph, like I just select something at random, the problem is that we don't want to find oftentimes with probability, we try to prove things with high probability. But the problem is that this is just a positive probability event, right? We're just saying that something happens with probability 69%. So in order to be able to do this, we really need a very precise description of the distribution associated with these eigenvalues. So this is just my opinion of why this problem is hard. Okay, so given that, I'll let you know our results. So the first one gives this optimal level of spectral rigidity. So I guess first you can see a consequence of our result. So first we show that the difference between lambda 2 and 2 is with high probability n to the minus 2/3 plus little sub n of 1. So this is this optimal rate of fluctuation. But actually, we show something stronger in that we show that with high probability, if I look at all of my eigenvalues, so lambda 1 through lambda n, once again, I'm going to throw out lambda 1 because I always know what it is. Then lambda k is very, very close to gamma k, which is where I would expect it to be based on this Keston-McKay law. And in fact, how close is it? Well, it's n to the minus 2/3 plus little of 1 times this other factor that gets smaller the closer I am to the bulk of the spectrum. So for example, if I'm interested in the middle eigenvalue, so like lambda n over 2, this says that the magnitude of lambda n over 2 is always going to be n to the minus 1 plus little of 1. So the order of fluctuation is even smaller than it is at the edge. Okay, so the point is that this rate of fluctuation is actually optimal. This matches what was conjectured in these computer tests, and also what's given by this other matrix ensemble, the Gaussian orthogonal ensemble, which once again is just like if I just have a random matrix where all of the entries are independent Gaussians. And just to compare it to some other work, so like I said, Huang and Yao previously achieved lambda k minus gamma k is at most n to the minus 1 over 100. And then in this other recent work, it's very nice work of Chen, Garza Vargas, Traub, and Van Handel, they gave a very short proof that gives a slightly weaker bound that these edge eigenvalues are always at most 2 plus n to the minus 1 over 6 plus little sub n of 1. So this is a weaker bound, but it's a very nice, very short proof. And also it generalizes to other types of graph models as well. So yeah, just to give a comparison here. Okay, so our second result is that we actually prove this conjecture given by Sarnak and then Miller, Novikov, and Sabelli. So specifically, we show that if I multiply by, let's see. Oh, okay, here we go. If I multiply by this factor of d times, oh, sorry. Yeah, here we go. If I multiply by this factor, then what I get converges to the Tracy-Woodham law. I just want to note here that this factor actually makes sense in the sense that this factor of d times d minus 1 over d minus 2 squared, this basically tells me the ratio of the number of eigenvalues near 2 in the Keston-McKay law and then the semicircular law. So the point is that if I want to reason about the fluctuation of eigenvalues, then it makes sense to normalize by this factor, which basically gives this ratio of the spectral density between the two models. Moreover, the same is true for minus lambda n, and also lambda 2 and minus lambda n are independent. And so what this means is that, in fact, a majority of D-regular graphs are done by part-height Ramanujan. This happens with probability about 69%. All right. So I think this ends the motivation part. So I can ask if there are any questions right now. Otherwise, I can move on to some of the methods. Okay. Then in that case, I can keep on going. But like I said, please let me know if there are any questions about what we're talking about.
Yeah, do you have any similar convergence for I don't know, lambda 3 or stuff like that?
That's a good question. So this generalizes as long as the index is fixed, right? So as long as I'm right at the edge of the spectrum, I can find the dynamics and show that it converges basically to what we'd expect. However, if I'm interested in like a bulk eigenvalue or really anything with index that increases with n, it's still open. Yeah. I would conjecture something similar, but yeah. Any other questions? Okay, great. So then I'll talk a little bit about the methods. Um, so let me first give a general overview. Like I said, I know that people are coming from a variety of different areas. So an overview of how we want to tackle this problem. So first of all, we want precise information about the distribution of eigenvalues. Traditionally, the first thing that was tried, and also probably this most common, purely combinatorial method, is to think about the distribution of the trace. So I take some high power of the adjacency operator and then look at the trace. However, this won't give us accurate enough information about the spectral distribution. So instead, what we're going to do is take a series of matrix inverses and find the traces of those. And this will give us very sharp information about the spectrum. Okay, the second problem that we need to think about is that thinking about the distribution over random regular graphs is actually a little bit tricky in the sense that it's very hard to find a bunch of independent actions associated with the graph. So if any of you are familiar with this Erdos-Renyi model where edges are included independently, oftentimes when I'm analyzing this model, what I'll do is think about the randomness associated with each edge and then combine it in some independent way. But the point is that in the random regular graph, actually edges aren't independent because the degree of every vertex is fixed. So what we do have, though, is another independence associated with this model, which is going to be the independence over edge switches. So we'll talk about this a bit more. And then the third problem is the one that I noted before, which is that we need to get very, very precise information. So we need to pass from a high probability bound to a constant probability bound. And the way that we're going to do this is basically using a dynamical equation and specifically analyze our model after we add a small amount of Gaussian noise. So this is probably the most technical part of what we do, but hopefully I'll at least be able to give some type of overview. Okay, so let's first talk about the Green's function. So like I mentioned, oftentimes a way to get spectral information is to calculate the trace, but this won't be accurate enough. So instead, we'll look at what's called the Green's function. So I'm going to take a real number z, sorry, a complex number z, important, where the imaginary part is positive. And then I'll take my operator and look at h minus z times the identity and take the inverse. So the point is that we know that h has real spectrum and z has positive imaginary part. So this is going to be an invertible matrix. Okay, so given the Green's function, I'll just give the normalized trace a specific name. So I'll call it the Stieltjes transform. So what that is, like I said, just the normalized trace. So 1 over n times the sum of the diagonal entries. So if I think about the trace as being the sum of our eigenvalues, then this will give me 1 over n times the sum of lambda I minus z quantity inverse. So I can think about this as some kind of average over my spectrum, also like a discrete integral. So more generally, if I have any real spectral density, I can define the Stieltjes transform of that density to be the integral over R of rho of x divided by x minus z dx. Okay, so how should we think about these Stieltjes transform? Like what information about the spectrum does it give me? Well, the thing to think about is that if I look at the imaginary part of the Stieltjes transform, this is going to roughly give me how many eigenvalues are distance at most eta from E. So here Z is equal to E plus I eta. And what we can see here is that if I just sum over all eigenvalues again, I get this quantity here. So if my eigenvalue is very close to E, specifically closer than eta, then the part of the sum will blow up. It'll be very large. Whereas if it's farther away than eta, then it will be smaller. So basically, this gives me some kind of smooth approximation of this indicator function of how many eigenvalues are very close to E. Another way to see this is if I fix eta and then I vary E, then I'll get some kind of smooth blow up every time I see an eigenvalue. And the width of the blow up is about eta. Okay, so what do we want to do? We're going to compare the Stieltjes transform for the Keston-McKay law with that of the random regular graph. And what we'll show actually is that we get convergence of this number to this other number for eta as small as possible, right? So if eta is a constant, this will give the weak convergence that we saw just from convergence of moments. But really, we're going to get this for eta is bigger than n to the minus 1. And the point is that this will give approximation in intervals of length approximately n to the minus 1, which is an optimally good size of interval. Because if you think about it, like I'm comparing a continuous object to a discrete object. So if I look at a spectral window of width less than n to the minus 1, there's no way that they can approximate each other. Okay, and so actually what we end up showing is that the Stieltjes transform for the random regular graph approximate that of the Keston-McKay law up to this optimally tight level. Basically, for any epsilon, these two are going to be close to each other with distance n to the epsilon over n eta. Okay, so how should I think about the Green's function and how do we actually use it in our analysis? Well, I think first and foremost, the Green's function we can think about as some kind of walk generating function. Because if I take minus z times I plus h and take the inverse, I can expand this in terms of powers of h. So what we can think about is basically giving different powers of our normalized adjacency operator with given some kind of complex weights. And oftentimes this is the analysis that we'll use where we'll say, okay, I have this contribution from one part of the graph versus another part of the graph. And we'll use the independence in our model in these different parts. However, this isn't going to be sufficient to do our analysis, basically because we want z to be very, very small. So this won't converge. So I need some other type of interpretation at the same time as this walk generating interpretation. And this is going to be this electromagnetic interpretation. And basically the idea here is just that the Green's function is like we're trying to solve the eigenvector equation. So we're trying to find an eigenvalue for something outside of the spectrum. And what this means is that G gives some kind of amalgamation of eigenvalues which are very close to whichever z we care about. And specifically, this will manifest itself in what's known as a word identity, which just says that if I sum the squared entries along a row, then this will equal to the imaginary part of the diagonal divided by eta. And the point is that inequalities or equalities that look like this word identity is what are going to help us to estimate just the trace. Okay, so actually, how are we going to use this? Well, the point is that if I look at the Green's function of the infinite tree, this satisfies a very nice recursion formula, which basically is derived from the Scher complement. But for the purposes of this talk, we can just think about it in terms of this walk generating function interpretation. And the idea is that the Green's function is just some inverse. So if I'm interested, for example, in walks that start and end at a vertex in my infinite tree, the idea is that there's a specific formula that allows me to write it in terms of walks on neighbors after I delete that vertex. And that's what's known as the Scher complement formula, and is given by this right-hand side here. But really, the idea is just that if I want to think about walks that start and end at a vertex in an infinite tree, I can just write that in terms of the first place that I leave, and then I must come back through that through that vertex. Okay, so why do we do this? Well, we can do the same process on after I've deleted this vertex. Specifically, I'll call that MSC. So this is like the infinite d-1 array rooted tree. And I can once again delete a vertex and then write it in terms of itself. Because when I delete a vertex of the d-1 array rooted tree, I get another version of it once again. So what this means is that I can write the Green's function at this root vertex in terms of itself in this very nice equation here, which we call the self-consistent equation. And in fact, this is actually the self-consistent equation of the semicircle law that we saw before. Okay, so big picture, what does this mean? What this means is that if I want to approximate the Keston-McKay law, which has to do with this infinite tree, it's actually easier to first pass to this infinite tree with a vertex removed and then looking at a root. And so we're going to take a graph approximation of that object. So specifically, we got the semicircle law by deleting a vertex and looking at its neighbor. So I'll just take the average of that over the entire graph. So I'll define Q to be the average over directed edges of deleting a vertex and then looking at the Green's function of the neighbor. And what I claim is that it's actually, first of all, sufficient to look at this object. And second of all, because this satisfies, the semicircle law satisfies the self-consistent equation, all we need to do is just show that this Green's function Q satisfies a similar type of self-consistent equation. And this is really what we spend the majority of the proof doing, is proving that Q satisfies this type of self-consistent equation up to some high level of accuracy. Okay, now let's talk about enlarging the probability space. So once again, the problem that we want to deal with here is that there are a lot of regular graphs, right? Basically, there are dn double factorial many graphs, d regular graphs and n vertices. And the tricky thing here is that entries of the matrix are not independent. So we need to find some action under which the distribution is independent. And this will be this idea of random edge swaps. So I start with some graph that looks like the left-hand side. I then copy it. And the idea is that I'll take two edges and then I'll switch their adjacency. And the point is that in the random regular graph distribution, these two graphs are equally likely to appear. Because if I have any two edges, it's equally likely that the edges appear like this versus like this. So they're equally likely that they appear parallel versus crossed. So what we're going to do is take the expectation over the random selection of these edge swaps. So how do we actually utilize this in our proof? We're going to do this by randomizing the neighborhood of a vertex. So I start with some vertex O. I then randomly sample the neighborhood. Or sorry, I randomly sample edges outside of the graph. I then will swap the edges, and what I'm left with is a new random neighborhood of O. So the idea is that I randomly sampled edges away from this vertex, just uniformly random throughout the entire graph, and then I swapped the adjacency. The point is that these two graphs, the original graph and the new graph, are equally likely to appear. So in this sense, I can randomize the neighborhood associated with this vertex O. And so the way that we'll think about this expectation is by further taking the expectation over this random edge swap. And really what we do is that we need to iterate this process. So I start by randomly selecting edges away from this vertex O, which will create a new boundary. And then I'll iterate this process by randomizing the boundary around this vertex C sub alpha as well. And what we're able to show is that we're able to do many resamplings, and every time that we do this, we can actually improve the error in our estimation. So in this previous work, Huang and Yao were able to take expectation over doing one edge swap, and they were able to sample over something like n to the log n many graphs. And in our work, we're actually able to sample over many more, like n to the n graphs, using this type of iteration. Okay, now finally, let's think about these Dyson-Schwinger equations. So this is probably the most technical part, but this is really what we have to do to get down to this precise Ramanujan bound. So the general idea is that there's a general method called Dyson-Brownian motion where we can show that the spectral statistics of some family of random graphs or random matrices more generally emulates that of a Gaussian matrix. And the idea of Dyson-Brownian motion is that I'm going to take my fixed matrix, so in our case, just the adjacency matrix, and then I'm going to add a small amount of Gaussian noise. And the idea is to track the change in the distribution as I pass from this original matrix to a small amount of Gaussian noise. So specifically, I'm just going to, just randomly do Brownian motion on individual entries of my matrix. And I'll do this in such a way such that at time t, my matrix is distributed such that I have my original matrix, and then I have a matrix with Gaussian entries, so this GOE, and I'm slowly replacing the original matrix with this Gaussian matrix. Now, given this, we're going to do what's called the three-step strategy of Dyson-Brownian motion. So the idea here is to show, first of all, that my eigenvalues have optimal rigidity. So this is like this theorem 1 that we showed before. Second of all, that after I add enough noise, I'm going to have these Tracy-Widom statistics that we're trying to show convergence to. And then finally, what we need to do is show that when I added this noise, I haven't actually changed my distribution that much. And this was the last thing that we had to show. And this is where we needed the tightest approximation, this step 3. And this is given in this proposition, which basically says that if I compare the Stieltjes transforms at time 0 and time t for some properly chosen t, then these two will be very, very close. Okay, so how do we actually do this? Well, we're going to use this self-consistent equation associated with the semicircular law. So the point is that what we were doing before is just showing very, very tight approximation to the semicircular law. But this level of approximation can never be achieved when we're comparing a discrete object, so an n by n matrix, with this infinite object, which is like the infinite tree. So what we actually need to pass to doing is comparing the finite object, so this n by n matrix, with another n by n matrix, which is just the Gaussian matrix. And basically, you can do this by what are called these Dyson-Schwinger equations, which are like more specific versions of the semicircular law, and are actually not too hard to derive. The hard part is then actually showing that our distribution approximates them. But I'll just say that the point is that you can write these equations down, and what we end up showing is that in our distribution, we approximate these types of equations in some very, very sharp level.
So is this related to Stein's method?
Yes, very much so, right? This is some kind of Stein formula that I have here, yeah. So really, we're just trying to show that the random regular graph matrix emulates this type of Stein formula, yeah. Okay, so this is what we end up showing. And then, okay, so to actually do this, we go back to this walk generating function type approach. So the idea is that we're really, if we want to compare Q minus YQ, we do this type of boundary resampling, and then we want to compare G of JJ remove I, and then Y of Q. And the idea here is that this is really trying to compare walks associated with two different graphs. So one is walks in the new random regular graph, and the other one is walks in this very simple graph, which is just a single vertex with two loops associated with it, both with weight Q. But the idea is to compare the Green's function. So once again, this walk generating function associated with these two different graphs. I just need to split these into different types of walks. So basically, where do I enter and exit the rest of the graph when I do a walk? So for example, this first term, G A alpha minus Q, is like saying I started at my vertex J, I then exit through one vertex, I walk around, and then come back through the same vertex. And the point is that this gives the comparison of doing this in my random regular graph, and then this type of idealized limit, which is like J with 2 loops. And however, there are other terms, right? Like it can exit here. I then can walk around, enter through the other vertex, and then come back down, which is like the second term. And then I could do something more complicated, like exit through one vertex and then come back again twice, etc. And then there are higher and higher order terms. However, the first order terms are going to be this form, which is like G tilde A alpha remove J minus Q. And the point is that when I do this random resampling, so when I randomly resample my neighborhood, this term is going to be approximately like if I just took a random edge in my graph and then took the value of gxx remove y. And the point is that this, if I actually do a true average of this is equal to Q. So this term should completely cancel. And then the second one, I should get something similar where I'm kind of taking a random entry of my Green's function, and that should approximately equal 0 as well. So this is the general heuristic that we use. However, a large part of our proof is really doing these somewhat technical calculations to show that these heuristics are actually true. Okay, so I'll just end by giving some future directions and open questions associated with this work. Okay, so yeah, as you've all mentioned earlier, or his question asked about this, is that like this really gives statistics at the edge of the spectrum. From a statistical physics perspective, it'd be quite interesting to also generalize this type of technique to the bulk of the spectrum. So for eigenvalue, for example, like lambda n over 2, for example. Also, you could think about something to do with eigenvectors as well. So this was done in a recent work, which applied the work that we talk about today to talk about the eigenvectors. And there's a simple question called the no gaps question, which basically asks, when I look at my eigenvector of a random regular graph, can I have a large part of that eigenvector which is very close to 0? Okay, so another question has to do with applying this to more general random graph models. So there have been a number of really nice works recently to do with random covers of graphs. So more general models, like something that looks like the right-hand side here. And the question is, can you apply this type of very sharp precision to something that looks like this? So for example, I think something that shouldn't be too much of a generalization of our current work is to show that with probability 83%, a random bipartite regular graph is Ramanujan, right? So just generalizing this result for non-bipartite graphs to the distribution over all bipartite graphs. I think further generalizations of this to something like what's done in these papers would be trickier, but that would be a good first step. Okay, something that gives a more computer science type perspective is that often we want to find spectral sparsifiers. So it's this idea that a random regular graph is like a spectral sparsifier of the complete graph. And so the question is, can we actually generalize this to sparsifiers of more general dense graphs? For example, if I have a hypercube, can I find some sparsifier of that? And maybe we can do this in some random way. And so, for example, in another recent work that I have, we generalized the type of techniques that we were talking about to infinite graphs, and this was used to prove a conjecture of Noga alone and Fenway. Okay, and then finally, I think another interesting question is, can we say that every graph is close to a Ramanujan graph? So the idea is, can I do a small number of switches such that if I start with any graph, I can get to a Ramanujan graph? And you could even think about doing this randomly, which then has to do with like the mixing time of the Markov chain. But the point is that all of our analysis has to do with taking the expectation over all graphs. And the question is, can I fix a graph and then just take the expectation over doing a random switch, which is kind of like what's done in Marcus Spielman and Srivastava. Okay, so just to conclude, we show eigenvalue rigidity for all eigenvalues of a random regular graph. We show Tracy-Whittem statistics for edge eigenvalues. This was previously known for when D is polynomial. And finally, most deregular graphs are Ramanujan. We use these very tight local Dyson-Schwinger equations, and then we also use a recursive formula for the Green's function to do with this iterated switching over and over again. So yeah, that's all I wanted to say. Thank you so much for your time.
Thank you, Theo, for the nice talk. Do we have a further question for Theo?
Can I ask a question?
Yes, please.
Could you please elaborate on the remark that graphs which can be embedded in Euclidean space are poor expanders?
Sure. I mean, this is just the idea that like if I think about, okay, a simple version of this, right, is just if I look at like the Cayley graph ZD, right? The point is that can never be an expander because like basically there's too much symmetry in the edges, right? Like if I want an expander, basically I need quick expansion of small neighborhoods, but I need that to expand quicker than any like Euclidean ball. Sometimes people actually think about these types of like random regular graphs as some kind of embedding into hyperbolic space. So maybe there's some cool way to do this where you actually take like a random embedding in hyperbolic space. But the point is that Euclidean space is actually, it doesn't expand quickly enough. If you wanted like a more rigorous version of what I'm saying, there's this paper by Justin Saleh who shows that if I have any infinite family of graphs with non-negative curvature, so for example, like Euclidean space, then that family cannot be expanders.
I see.
There's also the
Okay.
planar separator theorem.
Yeah.
So you can break the graph into two large pieces with only square root 10 edges.
Yeah, that's a more succinct way to say it, right? Yeah. Even if I just think about like the Cheeger inequality, right? Like I can partition if I can find a nice partitioning in Euclidean space, I'm not going to cut too many edges. Yeah.
Sounds good. Thank you.
Do we have other questions?
Yeah, so another question from the TCS side. If you wanted to construct like deterministically a Ramanujan graph, so do you think your approach can be de-randomized somehow?
Oh, that's a good question. Yeah, it would be nice to, I'm not sure. Yeah. I think probably it could, but I'm not sure how to do it. I think a good step would be like this last open problem that I said, right? Which is basically like even trying to think about making these choices sequentially is something that we're unable to do. We're really thinking about like a very holistic expectation over all random regular graphs. But yeah, if we were able to make individual choices in terms of edge swaps, then that would go a long way towards doing that. But yeah, that's definitely an interesting question.